Hello everyone. In this video, I can look at the examples of the modeling with the first order differential equations, especially the y prime equals k times y minus b, which is the rate of change. The differential equation describes a quantity whose rate of change of the y it's proportional to the difference of y minus b. So dy over dt equals k times y minus b. Okay. So this differential equation describes the quantity y whose rate of change is proportional to the difference y minus b. Okay. So we can use the separation. We can easily use separation variables to solve this differential equation easily and get this yt equals b plus cet. Okay, what we can do is you can just do dy equals dy over y minus b equals k dt. And then you take antiderivative on both sides. You get ln y minus b equals kt plus c, c1. So you can easily solve that at y minus b equals ekt plus c1, which is ekt times e to c1, which is another constant. You can use c, ekt, okay, and c equals e to c1 because they are constant. So then you solve that, you easily got y equals b plus c times ekt. Okay. Now the behavior of this yt, as t goes to infinity, we can easily tell if the k is positive, e to infinity power is infinity. When k is positive, ekt goes to infinity. When k is negative, ekt goes to 0. So ekt goes to 0, the y goes to a constant. Okay. So yt approaches the asymptote from the below, whether c is positive or c is above c is positive or negative. Okay, if k is positive, it goes to infinity. If k is negative, well, it will approaches to y equals b. Because ekt equals 0, if k is negative, t goes to infinity, e to negative power is 0. Okay, so the first model we're going to discuss is the Newton's law of cooling. Newton's law of cooling states the rate of change of object's temperature. The object's temperature is proportional to the difference between its own temperature and the ambient temperature, which is the room temperature or the temperature of its surroundings. Okay, if the object is in the refuge, so it's going to be the refuge temperature. If the object is in the room, is room temperature. Okay, that's what it means, the temperature of its surroundings. And T over T represents the temperature of the object as a function of time, because in different time the temperature change or varies based on the difference. So if the temperature of the room and temperature of the object is the same, then it doesn't change. Otherwise, the temperature, if it's too hot, it will cool down. If it's too cold, it will warm up based on the surrounding temperature, right? Then dt over dt represents the rate at which the temperature changes over the time. And the temperature of objects surrounding can be represented as Ts, which is the surrounding temperature. The Newton's law of cooling can be written as dt over dt equals k times T of T minus Ts. So we'll simply just write in this way. And the temperature of its object at the beginning of the experiment is the initial temperature. Well, normally we say that is called T0, is the initial temperature of the object. So therefore, initial value problem that needs to be solved, taken from this one. Okay, so this is the initial temperature of the objects. Okay, and then this is the differential equation we can set up for this for the Newton, based on the Newton law of cooling. K is a constant rate. Okay. Let's look at the first example. Example 1, net Y represents temperature of an object in Fahrenheit degree in a room whose temperature is kept constant 60 degree. If the object cools from 100 degree to 90 degree in 10 minutes, how much longer will it take for its temperature to decrease to 80 degrees? Okay. So based on the Newton's law of cooling, based on the above modeling, differential model, we can easily set up the temperature model is dT over small t equals, we don't know the K, and we minus the T surrounding area, surrounding temperature, but we do know that T0, we know Ts, the surrounding temperature, room temperature, which is 60 degree. We also know T0 is 100 degree. Okay. So based on this, we plug it in. We solve the equation. So you can set up dt over dt equals k times t object function t over t. I should say t over t based on the time minus the 60 degree. Okay. So we solve this one. Use the separation variables method. dt over t minus 60 equals k dt. Then you take the antiderivative. You got t equals you get t over t equals t plus, okay, we don't have the t, my bad. You got, let's just do it real quick. ln t minus 60 equals kt plus c. So solve that. T minus 60 equals ekt plus c1, just a constant. And solve that. T equals 60 plus c, which equals ekt times e to c1. So let c equals e to c1. c1 is a constant, okay? Both are constants, so c is also another constant. So c ekt. So now we have our solution is 60 plus c times ekt. Based on the condition t0 equals 100, plug that t0 into the function here. You got 100 equals 60 plus c times e to k times 0. E to k times 0, which is 1. So that's 60 plus c. And you solve 60 plus c equals 100. You got c equals 40. Okay. So once we solve c equals 40, now our function becomes to be t over t equals 60 plus 40 times e to kt. All right, so now we solve that. We have not used this condition yet. If the object cools from 100 to 90 into 10 minutes, based on t equals 10, then t10 equals 90 to solve k. All right, so we plug it in. 90 equals 60 plus 40 times e to 10 times k. And you got 30 equals 40 e times 10 to k. And you got e times e to the 10k equals 3 over 4. Take Ln. So 10k equals Ln 3 over 4. So you solve the k equals Ln 3 over 4 divided by 10. And that gives you the k equals negative 0.02877. Now we have our k solved. Now our final model is given now. So t over t is 60 plus 40 times e to negative 0.02877 t. And that's our model based on the given condition. Okay, the Newton law of cooling based on the given condition. All right, so now we need to solve. What do we need to do? We need to find out when does the temperature decrease to 80 degrees. So now we solve when t over t equals 80, and then what is the small t, right? So what do we do? We'll let 80 equals 60 plus 40 e to negative 0.02877 t. And we solve that, which is 20 equals 40 e to 0.02877 t. You get e to negative 0.02877 t equals 1/2. Take Ln on both sides, negative 0.02877 t equals Ln 1/2. And you solve t, which equals Ln 1/2 divided by negative 0.02877. That approximates 24.09 minutes. And the question asks you how much longer, okay, how much longer? So it has already been 10 minutes. So it will requires about 14.09 more minutes. Okay, for the object to cool to a temperature of 80 degrees Fahrenheit. Okay, so that is an example of a Newton's law of cooling.